So welcome everybody to the first quantum materials seminar. Thank you all for joining us and I hope you enjoy it. My name is Helena. I am the Quantum Materials Outreach Officer, which means that I help the Quantum Materials Research Group with all of their outreach work and public engagement work. And without further ado, I'm going to introduce our speaker today, Dr. Alexy Karenowska. So Alexy is a researcher in the Quantum Materials Group, and she does loads of cool research on all things to do with magnetism, which you'll hear a little bit about today. But not only that, but she's really involved in a lot of cool public engagement and outreach activities, a lot that span the breadth of both science and kind of cultural heritage. So if you're interested in that, be sure to check out her profiles on the physics website, and I'm sure she might be able to answer any questions about that as well. So I'll hand over to Alexy.
Thanks so much, Helena, and thanks to everybody for coming. It's a real pleasure to be here virtually this afternoon and to have the opportunity to talk to you a little bit, as Helena has said, about magnetism. So magnetism is sort of simultaneously familiar and mysterious. So we learn about it at primary school. We learn that about the lines of magnetic field that emanate from a magnet. We learn, so we're familiar with this kind of picture, so we learn about these lines of magnetic field, and we also know that like poles of magnets like these repel and unlike poles will attract. And people have been aware of magnetism as a phenomenon for literally thousands of years, and naturally occurring magnets in the form of magnetite, like in the picture there, can be found in certain parts of the world just lying on the ground. You can see those beautiful octahedral crystals. But magnetism is really hard to get at, right? It's very hard to understand from just looking at a magnet what magnetism is and where it comes from. And that's why the story of magnets and magnetism is arguably one of the most interesting in the history of physics. And magnetism has long been connected with the idea of kind of magic and mysticism, and even the word magnet has an origin that reflects the general mysteriousness or perceived mysteriousness of the effect. And in fact, there are two competing stories to explain the etymology of the word magnet. One is that it's connected to the Magnetes tribe in the ancient region of Magnesia. And Magnesia was eventually sort of absorbed into ancient Thessaly, but it was occupied by this tribe called the Magnetes. That if you're interested in classics, this tribe was involved in the siege of Troy. It was part of the Greek army. You can find reference to it in the Iliad. So that's one story. The other story is that the term comes from a shepherd whose name was Magnes, and this shepherd was walking on the side of Mount Ida. And he was there with his flock, everything was sort of going well, and then suddenly all the iron nails in his boots and the iron ferrule on his staff suddenly stuck to the side of the mountain, and Magnes had discovered magnetism. So I'll leave you to decide which story you would like to believe. But what's interesting is that this is not a sort of mysteriousness that was perceived in the classical period and then kind of went away. Even when you understand what it is, magnetism still doesn't kind of lose its magic. Maybe I'm a little bit biased, I work on magnetism, but it still seems kind of incredible that it happens. And against the backdrop of really an extremely early recognition of magnetism as a phenomenon, it really did take a very long time for the principles of magnetic science to be worked out. And actually, the satirist, famous American satirist called Ambrose Bierce, wrote at the beginning of the 20th century about this. And he made a comment that I like very much. So in his Devil's Dictionary, which you might like to look up if you don't know it, it's a book that's available free online, he gave the following definitions of magnet and magnetism. So he described magnet as something acted upon by a magnetism. And then he described below it magnetism as something acting upon a magnet. And then he added the comment, the two definitions immediately foregoing are condensed from the works of 1,000 eminent scientists who have illuminated the subject with a great white light to the inexpressible knowledge, advancement of human knowledge. Now, that was a little bit mean. He was writing in 1906. He'd made quite a bit of progress by then, but I think it captures the spirit of the science. One actually interesting fact about Ambrose Bierce, which has absolutely nothing to do with physics, is that he was one of 13 children, all of whom were given names by their parents beginning with the letter A. Now, it's not clear whether that was something that was a question of principle or practicality, but it's a fun fact. Now, there are lots of old wives' tales, or there were, around that started around the classical period and lasted for many hundreds of years about magnetism. People believed, for example, or would say that garlic, diamonds, and onions stopped magnets from working. It's a kind of interesting idea. And there was a school of thought that persisted for a long time that magnetism had its origin in the stars, and in particular the constellation of Ursa Minor, the little bear that has the North Star Polaris in it. And this was an idea that was very much supported by quite an important Italian academic called Ficino in the 15th century. And there was also this interesting question of whether electricity and magnetism were in some way connected. Now, remarkably, this is a question that was pondered as early as 500 BC. And it's said that the great philosopher Thales, this is a much later rendition of him, thought that the two could be connected, electricity and magnetism, on account of the kind of similarity between the force of attraction that's experienced by something like a feather or some dust to a piece of amber that's been rubbed, so that's the phenomenon we now know as static electricity, and the attraction between two magnets. Now, of course, we can argue that this was sort of a case of a chap who had an interesting idea for all the wrong reasons. But then again, really many interesting questions in physics start out like that. And I think it is right to say that this was the beginning of a debate that would go on for no less than 2,300 years. Now, it is a big leap from Thales to Ørsted, and there were a great many brilliant minds that occupied the gap in between, but it was his experiments in the 1820s that made it possible to resolve finally this question of whether electricity and magnetism are linked. And he observed, actually by accident, that a compass needle was deflected by a current flow, or when a current flowed in a wire next to it. And thus he was able to show that electrical currents give rise to magnetic fields. And then after him, the great James Clerk Maxwell went on in the 1860s to construct one of the most remarkable and most beautiful pieces of theoretical physics ever generated. And he effectively invented the science of what we now know as electromagnetism. There's a great picture of him here with his wife, Catherine, and an extremely fluffy dog. Now, so electromagnetic waves are propagating waves that are characterized by electrical and magnetic waves that move at right angles to one another. And there's a sort of a representation of one in the middle of the slide there. And these days, I think it's hard to imagine life without electromagnetism. So we use it every day, right? It's literally making this seminar visible. It underpins the technology behind our mobile phones, our microwaves, and a whole host of medical and scientific equipment. But it's not the only wave-like effect in magnetism. And my work in the lab involves, in fact, a quite different kind of magnetic wave. And that's what I want to talk a bit about this afternoon. And to understand what it is and where to find it, we need to know just a little bit about where the phenomenon we know as magnetism comes from. Now, in sort of general conversation, we tend to use the term to describe permanent magnets, so bits of material like this that will stick to your fridge and attract and repel each other. But in fact, all materials respond in some way to magnetic fields. Now, most materials are what we call diamagnetic, and that means if you apply a magnetic field to them, they produce their own weak magnetic field to oppose it. Then a much smaller group of materials, the best known of which is iron, show a behavior that we know as ferromagnetism. Now, if you apply a magnetic field to a ferromagnet, it will generate its own magnetic field in the same direction as the field that you've applied. And when you take the field away, it'll stay put. And this is the effect that we're generally referring to, as I say, when we talk about magnetism in our everyday conversations. So where does it come from? Well, ferromagnetism has its origin in the electronic systems of magnetic materials. And in particular, we see it in materials that have unpaired electrons in their outer orbitals. And I'm going to try and use this cartoon here to illustrate why that is. So electrons have a property that we call spin. And you can think of spin as a sort of quantum mechanical currency of magnetism. Because the electrons carry a spin, they're effectively, as you can think of them, like little bar magnets. Now, the rules that govern the way that electrons are organized in materials, in the orbitals of materials, the orbitals of atoms of different materials, mean that the electrons generally pair up. So this means they pair in such a way that the net magnetic effect is zero. So they pair in such a way that two electrons of opposite spin, you can think of them as like little magnets pointing in different directions, go together, and so their effect cancels each other out. Now, in ferromagnets, there are unpaired electrons, and as a result, we get what we call a magnetic moment, a net magnetic effect associated with the atom of the material. So, what does it have to do with spin waves? Well, you can imagine a ferromagnetic material, a permanently magnetic material, as a kind of 3D network of miniature magnets. And these magnets interact. So that is, they feel forces from one another's associated magnetic fields. And so the whole system looks a little bit like the picture on the slide there. It's like a kind of magnetic equivalent of a series of little masses, the magnets, connected by springs. That's the magnetic interactions between them. Now, you know what would happen if you flicked the structure on the right of the slide, the mechanical structure, right? You get mechanical vibrations that would propagate through it. Now, exactly the same is true of the structure on the other side of the slide, on the magnetic structure. If you give it the magnetic equivalent of a kind of flick, that is, you tickle it with a little magnetic field, what you get is a magnetic wave that propagates through the structure, and that's a spin wave. So, to some extent, a spin wave is just like the kind of magnetic equivalent of a water wave. It's a wave, but rather than being defined by a kind of moving variation in height of water, like a water wave is, it's defined by a moving variation in strength of magnetic field, the same stuff that sticks your fridge magnet to the fridge. And it turns out that this analogy is actually more than just useful for our kind of understanding. It's also really helpful if we're interested in studying the more exotic aspects of general wave dynamics. Now, the picture on the slide here shows the Severn Bore. Now, this is an interesting tidal phenomenon that sweeps periodically down the River Severn. Now, it's a really interesting nonlinear effect. It happens because of the nonlinearity of water. And you can see that it involves a kind of strong leading wave followed by a train of smaller ones. Now, people study these kinds of effects, and it's very interesting, but if you want to do it actually on the water, you have to have a lot of patience and a stout pair of Wellingtons and probably some sandwiches as well. But it turns out that if you're not the outdoors sort, you can actually recreate this very same phenomenon in the laboratory. And I'm going to show you that inside a piece of magnetic material. So here it is. This is an experiment where we have a little piece of magnetic material through which spin waves can propagate. And what I'm going to show you is a wave propagating from one of the antennas here in the structure to the other side, to the other antenna. And this is data that's been collected optically. Okay, here we go. So, this to play. So you can see that the wave propagates through the material in just the same way as the Severn Bore. Now, this has been slowed down quite a lot, okay? So this video is actually, the duration that you're being shown the data for is 100 nanoseconds. You can't really surf on something that travels that fast, but I think you get the idea, right? We're able to recreate these effects using spin wave systems as a really helpful model system, a model environment. And we can further capture and use this same physics, so the high speed propagation of spin wave through tiny pieces of magnetic materials, together with their really exotic and interesting behaviors. And this kind of tidal bore-like wave is just one example of a whole host of really interesting wave effects that we can see of these systems, to develop new kinds of information processing devices. And these are systems that can have all sorts of interesting advantages over today's state of the art. And that is exactly the work that goes on in my lab. So when you get the quiz question, what connects the Trojan War, the Severn Bore, and electronic devices that are so new that they haven't even been invented yet, though others may struggle, you will all know the answer. It's the spin wave. Thanks so much. I'd love to answer your questions. I'll finish there.
Thank you so much, Alexy, for that short but very sweet introduction to the world of magnetism and your work on spin waves.
Oh, it's a real pleasure.
Amazing. So I think, great. So we're getting some questions coming through, which is...
It's gone wild here.
Oh, and some of them are getting upvotes. Fantastic. Right. So let's start with the one with the most upvotes from an anonymous attendee. How do electromagnetic waves travel through a vacuum with no magnetic field?
So that's a really good question. So electromagnetic waves are by nature able to travel through space. They don't require a medium to propagate. Essentially, they are they consist of electrical and magnetic energy. So they don't need a medium to propagate through, which is, of course, you know, it's easy to take that for granted as a fact, but it's an extremely empowering phenomenon. It makes the electromagnetic wave an extremely empowering phenomenon. You know, we can talk to spacecraft in space because of this particular convenience of physics. We can see distant stars and planets for the same reason.
Yeah, fantastic. It's a property that we take for granted.
Yeah, that's right. Yeah, it's very easy to take it for granted, and such a new science as well. I think this is really, I think it's very easy to think that this is science that has been around for a long time, but of course it's not. It's 19th century physics, and even, you know, the beginning of the general understanding of magnetism is quite young. I mean, compasses, for example, are a 13th century phenomenon. I think a lot of people, at least in the West, in the Far East, it's probably not the case, but people didn't start to use and understand compasses for navigation until the 13th century.
Amazing, thank you. So we've got another really good question here from Duncan. If ferromagnetism is caused by unpaired electrons, then why don't non-metals with unpaired electrons also show ferromagnetism? Okay,
that's a really good question. So like all situations in physics, it's a little bit more complicated than I've suggested in the course of this talk. So particularly, there exist non-metals that are magnetic, and in fact, some of the most important commercial magnets are non-metals. So these, for example, these magnets, which are just a typical kind of, children's toy, I guess, are samarium cobalt, I think. And there's a whole range of ceramic materials that do display magnetic effects. But once you get into non-elemental magnets, then the precise detail of the electronic structure becomes really important. But essentially, all magnets can be described as a kind of equivalent atom or molecule that has some number of unpaired electrons? I realize that's a bit of a fluffy answer. It's a really good question. And that's why you should become a magnetician if you're not already.
Yeah, that sounds like a really good string of research for that sort of thing, finding new magnetic materials.
Exactly. Yeah, that's right. Yeah.
Amazing. So keeping on with the theme of thinking about ferromagnets, so we've got another question here from John. What is it about the orbitals in iron, cobalt, and nickel that make them so strongly ferromagnetic?
So that's a good question. It has to do really with the the strength of the magnetic effect has to do with a parameter called the exchange effect in the material, in the atom. So there are two magnetic effects that are important to magnetism. One is called the dipole interaction, which has a classical analog. So that's just the fancy word for the expression that for the force that you feel between two magnets, two magnetic dipoles. There's also the exchange effect. The exchange effect is very, very important to setting up ferromagnetism in materials. It doesn't have a classical analog. It's a quantum mechanical phenomenon that has to do with the rules that govern the symmetries of overlapping electron orbitals in materials. So again, it's a really good question that strikes right at the heart of why magnetism is interesting. But unfortunately, it doesn't have a hand-waving answer. You have to dive deep into the physics of the interactions between the electrons in the system.
Yeah, you definitely need your undergrad quantum mechanics courses for that sort of thing.
Yes, exactly. Yeah.
Amazing. Yeah, just one of the many reasons to study quantum mechanics.
Exactly.
So another sort of research-based question here, which has got a lot of upvotes from Gracie. So how exactly are we using magnetism in new electronics?
So in all sorts, that's another great question. These are great questions. So there are several answers to that. One important thing to recognize is that actually until very, very recently, magnetism has been absolutely central to the way that home computing works. So our computers are increasingly going solid state, right? So our hard drives are now, we're moving towards a situation where almost most computers have solid state hard drives. But the traditional hard drive, which is based on a disk, people have probably seen those beautiful shiny silicon disks, is actually encoded magnetically. So the science of spintronics, which is all about the control of currents of electrons and other carriers based on their spin, underpins that hard disk technology. In fact, most importantly, underpins the ability to read the bits. So there was a time in the 1990s where information could be written onto disks with a greater density than it could be read. And the development of spintronics, which led to the development of an understanding of an effect called giant magnetoresistance, led to the development of sensors that enable very densely packed magnetic bits to be read. So I think sometimes that surprises people. They think, magnetism and electronics are something, that haven't sort of reached our shelves yet. But the contrary, this is it's very, very important to our current electronics. There are lots of ways, though, that magnetism can potentially have an impact on next generation electronics. So spin waves are interesting in this context for a number of reasons. Firstly, I didn't touch on this in the talk, but they can propagate through magnetic insulators. So somebody mentioned magnetic insulators in an earlier question. Not all magnetic materials are metallic. And in fact, there are some important rare earth magnets. And so these are materials that look a bit like garnet. People come across the kind of red and green stones that you get in jewelry. Materials look just like that, but they're strongly magnetic. And these magnetic waves, the spin waves, can propagate almost without dissipation through those materials. And this is really important, or potentially important, because as people will be aware, one of the biggest problems in contemporary electronics is the heat death phenomenon. So the difficulty is that your computer, the performance of your computer is limited now not by the clock speeds that can be achieved or the density with which transistors can be packed, but by the fact that basically it'll cook itself, because the thing generates so much heat because of ohmic losses that it would just melt if you were to build, or it would melt.
Mine's absolutely overheating already with just this Zoom.
No, absolutely. So one of the areas in which magnetism holds quite a lot of promise is essentially in developing signaling systems in which their charge currents don't have to propagate, and there are no ohmic losses.
Wow, that's great. So I think we're almost done, but I think we'll just have one more question, and this might be a little bit of a bigger question. This is from Amanda. Why do electromagnetic waves have a finite speed?
Okay, so that's a great one to end on. Okay, so there are two answers to this question, both of them equally unsatisfactory, right? So the first answer to the question is, well, if you look at the rules that describe the propagation of electromagnetic waves, and in fact, if you look at the wave equation generally, the way that the speed is defined essentially is leads you to the constant, if you see what I mean. So essentially, you when you do the mathematics, what pops out of that mathematics is actually the conclusion that the velocity of the waves is finite. It depends on the medium for any wave. So for an electromagnetic wave, you can slow light down by propagating it through something that has a finite refractive index, most things. But it can't exceed the speed of light in free space, in a vacuum. And that is set in stone by essentially the electromagnetic properties of the vacuum. Now, that's an unsatisfactory answer, because if you unpick it, it basically says, well, it's just because, right?
Just because
yeah. So the other unsatisfactory answer is to say, wow, what a really interesting, philosophical question. So, why? There are different kinds of why, right? We can unpick the mechanics of why it is, and I can show you some quite sophisticated maths, to describe exactly why you come out with this finite speed. But, thinking about the deeper question of why should it be the case that the laws of nature are such that we end up with electromagnetic waves having a bound on their velocity is a much deeper and more interesting question, and probably strikes at the heart of why physics is such an exciting world to work in, and why an appreciation of physics is always so humbling.
Amazing. So we're going to end with a bit of philosophical thoughts
Yes.
on physics there. Fantastic. What a way to bring the first seminar to a close. Thank you so much, Alexy.
No, it's a huge pleasure.